Okay, let's get started on another exam problem. This is exam 2 from spring 2017, and this is problem 3. So, if we read the question, it states the distributed load acts on the beam AB as shown, as we've got here. The two-part question, part A is asking for determine the force couple system at point A that is equivalent to the original distributed load. Replace the original distributed load with an equivalent resultant force and specify its location measured from point A. So that seems not too difficult. Maybe some confusing words in there like force couple system. When I first read that, I kind of thought, what was that? But hopefully we'll figure it out. Basically, if you look down here at what it's asking for at the bottom right, it tells you exactly what it wants. It wants the resultant force of the distributed load, and it wants the moment from that load at A. Or the moment, I guess, from everything at A, but that load, essentially. And then part B is, again, I believe it would be the same resultant force, and you would therefore use that to find the distance from point A, using moments. So that's not too challenging of stuff. So first we want to start at part A. Determine the force couple system at point A that is equivalent to the original distributed load. And this is where it kind of gets a little tricky because we've got a lot of distributed loads we got to work with here. So let's take a look at this. We can split this off into multiple distributed loads to make it easier for us to add. I'm just going to draw some sketches. Actually, I'm going to get a colored pen out and draw some sketches on here that might make it a little bit easier to see. So here we have 2 kilonewton meters, and this is also 2 kilonewton meters. So if we draw along here, this is going to be, we can look at this as its own distributed load right here. Anything under this orange line. And then we also have these 2 triangles up here. So we're going to separate these out here. I'm just going to draw as much orange as we can to separate that. So essentially we've got 3 shapes here, 3 distributed loads acting as one, if that makes sense. It might not how I just said it, but essentially we can find the area of all of these objects to find what our total distributed load is. Because distributed load, because it's kilonewtons per meter, it's cumulative. It adds the longer in you go. And if you use units, you can kind of see that when you multiply the height of this by the base, it's 2 kilonewton per meters. Multiply that by 6 meters, and you're just going to get kilonewtons. That's going to be your load. So I'm going to label these shapes. Let's say we have A, B, and C, and we just want to find the area. So area of A, we're going to have 2 kilonewton meters. It's going to be times, that's 6 meters plus 8 meters. That's 14 meters total. And just want to display that we can cross out the meters. That's going to be equal to 28 kilonewtons. And so we've got that. And we want to know what the distance from A is that it's having there. So the distance from A, whenever you have rectangular distributed loads, the resultant force, you would always say, is acting kind of in the middle. And this arrow I drew here is just for this one here at the bottom. But it's always in the middle. So it would be acting, if this is 14 here, it would be acting about 7 meters from A. So we'll just go ahead and write that. So we've got that. And we can go ahead and do area of B. And what we have here, this is a triangle. We want base times the height. So the base we have is 6 meters. The height is going to be, we have this 8 kilonewtons per meter up top here. But you want to be careful. You don't want to just use this 8 because that's not the entire height of the triangle. We want to make sure we stop it at the 2. So it's going to be 8 minus 2 kilonewtons per meter. And then we're going to multiply that out by our 6 meters. And because this is a triangle, we're going to want to divide that by 2 there. And so 6 times 6 is 36, divided by 2. I'm going to check, it should be 18, but I just want to be safe. So, yeah, it's 18. So we've got 18 kilonewtons. And that's what we've got there. And as far as where this is acting, let's see, with triangles, the resultant force always acts 1/3 from the tall end or 2/3 from the far end. And I believe your lecture video should have gotten into why that is, but ultimately you just have to memorize that. Unless you're a calculus master and want to do calculus on this exam, which I do not want to, it's best if you just kind of memorize where these would be acting. And so if we take it 2/3 away from this end, it would mean it's 4 meters from A. And then we'll go ahead and take area of C. And this is again going to be 8 minus 2 kilonewton meters. And this time our base is going to be 8 meters. And divide that again by 2 because it's a whole triangle here. We do that. It's going to be 6 times 8 divided by 2. We got 24 kilonewtons. And from A, it would be, I like to put it from the distance from A. The reason I'm putting these distances from A is, first of all, it's just a good rule of thumb, and I'm using A as a reference point. But I chose A specifically because we want the force couple system at A. And so that means we want the moment caused by this at A. If we wanted it at B, I would use the reference how many meters from B. But here we're doing it from A. And so from A, our distance, again, the force is going to be acting, or the resultant is going to be about 2/3 of this base here away from the tall end. It's going to be somewhere kind of like that. I should have drawn an arrow for the other one here. It'd be kind of somewhere in there. But somewhere kind of like that. But we also want to take into account the 6 meters here. So I'm going to just go ahead, 6 plus, and if it's 1/3 from the tall end, we'll just write 8/3 meters. I always like to write out my math and make sure I can be as thorough as I can. 8/3, if we calculate that out, 6 plus 8/3, we get about 8.667 meters from A, 0.667 meters from A. So now we want to know what our resultant force is. The force coupled system at A. Now, one thing is it's asking, it looks like it's asking for the force, the resultant force in vector format. But if we take a look at this, all of these would be in the y direction because the distributed load is just pointing down. If we take a look, the distributed load that acts, determine the force coupled system at A that is equivalent to the original distributed load. And so we're just worrying about the distributed load. It's pointing down. We don't have to worry about, I know B does have a lateral force, but we don't have to worry about that. If we did a free body diagram of this beam, we'd find out that the X force of B would be 0 anyway because there's no other forces acting that way. And so when it's asking for the magnitude, or the vector format, we basically just know it's going to be 0I because there's nothing in the X. And then as far as the J, everything acting in the Y, we're going to want to add up all of these areas we found. And so to find the resultant force in that direction, we're going to want to take our 28 plus 18 plus the 24. These are all the moments that we found before. And those happen to equal 70 kilonewtons down total. And that's just a good reference when you just add that. So in our answer box down here, because they're going down, we're going to write minus 70J, and we're going to want newtons. And that should be our answer for the resultant force in vector format there. As far as the moment about A, this is kind of where it gets tricky. We have all of these different distances here. So what you're going to want to do to find the moment about A is you're going to want to multiply each of these resultant forces that we found by the distances from A. And then that should give you your total moment. So down here, and it looks like it's asking for just the magnitude. We probably want direction as well, whether it's positive or negative, but it's not asking for it in vector format, which is nice. So we'll go over here, MRA, and that is going to be equal to, we'll start with this, we've got our 28 kilonewtons, which is acting kind of in the middle here. That's going to be 7 meters, and that's going to be negative. And so we've got 28 times 7. And then over here you've got our 18 times our 4 meters. The 18 here times the 4 meters are here. So it's going to be minus 18 times 4. And then I'm going to draw a little separating line here so maybe clarify a little bit more. We've got our 24 that's acting 8.667. So again, we'll take minus 24, 8.667. And when we add these all up, that'll give us what our moment is, or our kind of force couple system. So if we take a look, we've got, I'm just going to do these in positive on my calculator because they're all negative. So we know that 28 times 7 plus 18 times 4 plus 24 times 8.66667. I like to add a lot of sig figs whenever we do something like that. My bad, you couldn't see my calculator, but here's what I have. And that gives us about 476. Negative 476. Again, this is going to be kilonewtons times meters. So down here, negative 476 kilonewtons times meters. Now, honestly, it doesn't tell us if it wants like magnitude or direction or whatnot, but I'm going to go ahead and include the negative sign on this one. I'm not entirely sure if that's what they're getting at or not, but just logically using right-hand rule, we can see that they're all about A having a negative moment, clockwise moment, therefore negative. So that's what we're going to have here. So we can go ahead and separate that off. Now we can start at part B. And so part B says replace the original distributed load with an equivalent resultant force and specify its location measured from point A. As far as I can tell, this is going to be the same force that we had from part A, because the force couple is basically just asking the total force of this distributed load and the moment that's being caused by it. It's the same force. I don't know if there would be another force that we could have here, to be honest. So the same force here, we're just going to go ahead and copy that down. Minus 70 J newtons. And we can maybe write this up here just for reference. F R equals 0, I minus 70 J newtons. And what it's also asking is specify its location measured from point A. So we're going to want to replace, we're basically trying to replace this entire thing by just one single force. Just to give it the same moment about A and the same total load. So to do that, we're going to want to use our equation that's given in your equation sheet. Again, I highly recommend you learn your equation sheet. But we have the moment of a force about point O is equal to, in this case we can just use the scalar. Moment is equal to force times distance. And so I would highly suggest always writing in your videos, or I'm sorry, not writing in your videos, writing in your equations that you're going to use. Just so the grader knows what you're looking at and just so you know what you're thinking about in reference when you're doing the problem. Kind of works both ways in being helpful. So let's see here. Our moment is still going to be the 467 because that's what we found was caused by this entire distributed load. So we're going to have, I'm going to write it as negative 4, or did I say 467? 476. Kind of eating my words here. And then as far as these, force times distance, we have force. We only want to worry about, and this is the only force that we really have to worry about but we only want to worry about the force in the y direction. There is no force in the x direction to cause a moment. And in similar questions like these, like some of those of you who took the quiz a couple weeks ago, where they wanted you to replace all the forces with one single force. When it's acting on the beam here, the x shouldn't really matter because it's on the beam. It wouldn't cause a moment. So right here, we're just using our y force here. We're going to put in our negative 70. Oh, my bad. Have I been writing newtons this whole time? Everything has been in kilonewtons. And so when I wrote newtons down here, this should be in kilonewtons. This should be kilonewtons. So go ahead and put kilonewtons in here, and then multiplied by our distance. And so it's algebra from here on. You're going to find that your distance is going to be equal to, and again, these are both negative, so it'll end up being positive. It's going to be our 476 divided by 70. And if we get that, looks like it's 6.8. 6.8 meters from A. So we go down here, x, I wrote it as d, it could be x as well, 6.8 meters. And as far as I can tell, place the original distributed load and specify its location. This should be the entire problem then. So we found what the forces were total caused by the distributed load, and we found the distances of each distributed load resultant from A to find what the moment about A was. And then using that moment about A, we took that and divided it by the total resultant force to find out where we could replace the entire load with just one force. So I hope this all made sense. If you guys have any questions, always feel free to email me or whatnot and let me know. I hope you guys have a good luck studying. I hope you guys do well on this exam on Tuesday. So have a good one.